Hello everyone, I'm Xuanzhi. I'm going to share you with my work on causal discovery collaborating with the DMI lab. So causal discovery or causal network learning, I would like to start it with the context in brain science. In order to understand the brain function, one of the popular way is to do a network mapping of the brain structure. And the first step of the mapping is to define a node in our brain. So the node I mentioned here are spatial regions of interest for ROI in case of functional MRI data. If we give such a causal significance behind the data, that is, in the brain, we assume that region A might have some, causal impacts on region B. So given the sense we are carrying, can we discover something like a brain network? And typically, chances are we will forget or fail to observe some of the regions, which will make it the unknown common factor or Latent Confounders in terminology. So Latent Confounder will increase some elusive dependence between our observational regions. So given the well-known nonlinear connection in brain functions, something like a dynamic causal model, so that is exactly what we're carrying in this paper. Or in other words, given the data, can we identify a causal network? And speaking of causal identification, we have the PT algorithm, which based on the Bayesian network analysis, putting the causal constraints on the mapping between the probability side and the graphical side. And we also have the Lingang and CNN method, putting more constraint on the mapping itself. We expected something like a causal nonlinear function. And when it comes to the problems of Latent Confounder, our previous work, MLC Lingang, sort of combined the advantage of these two methods. And on top of that, we have the CNN UV approach. It suggested that we can identify the cause and effect, or the capital C and capital E here for these two nodes. We can do this by illustrating a latent variable pace, and latent variable here I mark it as the yellow color. But we are still wondering, aside for the illustration, can we make a clear condition? And specifically, how can we fix it into our context Latent Confounder? So to do this, we break it down into two cases where we specify this is about the graphical language, the parents, the observed parents or PAE here, and the unobserved parents or PAC bar here. So you see here is sort of like the indirect unobserved confounding, right? And likewise, we can flip around the situation. So the next step is we can apply the famous assumptions and statistical methods in causation in both the two directions, from the cause to effect or from the effect to cause. But we discovered that only for this case, we will find the statistical asymmetry in these two directions. That is, independence on one direction and dependence on the other. So that asymmetry sort of gives us an evidence to identify the causal relations here. And you probably noticed that if we put both of the parents to be unobserved, that is generally the latent confounding setting, right? But here, we want to clearly divide into two cases because that involves the most important idea in this paper. Our work largely depends on the additive noise model, or ANN, but in this paper, we propose a latent ANN, and we develop this idea in both the theory side and the algorithm side. I'm not going to stay too long in this line. Let me quickly show the point. Given the data generation, this is roughly like the AM model. But notice that here we incorporated the nonlinear inference of the unobserved parents or unobserved factor with the independent noise so that we got extensive noise. And notice that the extensive noise here does not necessarily to be an independent one. And that is exactly the point about how we modeling the latent confounding in this paper. And with the big algebra, we have an expansion equation like this. And the reason for doing this is to teach the machine to do some regression on the left side in order to make the extensive noise on the right side to be independent again. And this is sort of like an optimizing procedure. And notice that the extensive noise is like a dynamic change one, right? So in order to make it to be independent, because that independence is exactly required by the identifiable condition we propose in this paper. So in the next, let me quickly show you some intuition about that condition. Say we are still interested in identifying the causal relations here, but in the same time, we definitely have some other, multiple cause of the effect, which are observed or unobserved. We have no idea. But the tricky point is we are also not quite sure about the relations between the interesting cause and this boundary of cause here. And that simple with two little circles here is that we might have the direction going like this or the opposite one. But again, we will specify the unobserved parent, and we sort of summarize the rest of the observed variables into here. We use that with the capital U here like this, and then we combine the unobserved parents and the noise to be the extensive noise, and specifically the extensive noise of the effect. And here I will just show you the condition quickly in the below. And that means if you just list out all of the possible paths from the interesting cause to the variables u, is sort of like a hub to the variables u and to the extensive noise. Then if you can sure the cause here is independent of the extensive noise, then the condition will tell you the correlations between cause and effect is identifiable. Or in other words, if you are familiar with the notions of deseparation, it's equal to say the deseparation set between the cause and the extensive noise should be an empty set. And the reason that is because the nonlinearity. Notice that that is not a compulsion in linear discovery, but that will involve some details. Let's just focus on the big picture here. So equipped with this condition, if we have a causal diagram and with some Latent confounding here, so given the data generated by such a structure, if we want to estimate a causal graph, we will first step learn a causal scaling with spurious edges, and then the second step, we break it down the scaling into several units, where each of the units we will apply causal inference based on our identifiable condition. And two of the interesting point in this line is that, first of all, even before you apply the algorithm by use the condition here, you can still quickly determine which the edges is essentially unidentifiable. And the second step is that, and the second point is that after you applying the algorithm, the unit that consisting the unidentifiable edges is essentially the unit that consisting the superior edges. So that sort of help us, back into our ground truth that sort of help us detect the location of the Latent confounder. Okay, to evaluate our method, we will go back to the functional MRI data, and this time we use a bit complicated structure. We test our method by increasing the numbers of the Latent confounder. And although we got a bit lower in the record because in the first step we learned a causal scaling, so we are focusing on more lower record and sparse graph structure. But comprehensively, we got a big advantage on the F1 score. And by the way, our method greatly reduced the computational cost. So if you want to get started, you can head it to the Caltimark. This is the Python package that we developed for this algorithm. And before I wrap up this video, I want to borrow a sentence from the popular causal book, Elements of Causal Inference. So a quote here: causal methods that quite follow the proofs are often insufficient in making use of the data. So although we did provide some theoretical identifiable condition, but general and more personally, I wish the algorithm to be a practical tool. So for researchers who are just interested in nonlinear causal discovery, I hope we can just apply the algorithms and give it a shot, see what's interesting will be discovered. Okay, thanks for your watching.